Okay, so we're going to go ahead and go into our next example. And this is going to be on figure 9.19 here. And we want to calculate the force of the right arm or right hand. So the force exerted by the right hand and then the force exerted by the left hand. Okay, given that the hands are 0.9 meters apart. Okay, so we can say R1 is equal to 0.9 meters. And the center of gravity of the pole is 0.6 meters from the left hand. So I'm just going to call that R2. Okay, the pole is uniform and it has a mass of 5 kilograms. Okay, so what we'll need to do in order to solve for the force exerted by the right hand, we're going to make a few claims. Okay, so first of all, we know that this is going to be at equilibrium. Okay, so we're going to say that our net torque here is equal to 0. Okay, also we need to pick a pivot point. So what I'm going to do is I'm going to go ahead and pick my left hand as my pivot point. Okay, so this is my pivot point. Okay, and remember that our pivot point, that will tell us that our torque there is going to be 0. Okay, and the reason is because our radius is 0. Okay, if we're claiming that that is our starting point here. Okay, our pivot point. Okay, so let's go ahead and go off of that. Now we need to define our motion here. So our torque of our right hand and of our center of gravity point here. Okay, we need to find those. And in order to do so, we need to define our motion. So if we have our clockwise motion here, so clockwise, we're going to say that that's the positive direction, okay, and that our counterclockwise direction is going to be negative, our negative direction. Okay, so based on that, we can go ahead and set this up. So we have our counterclockwise, we can say our net tau clockwise motion should be equal to our negative net counterclockwise torque. Okay, or we can say net torque clockwise plus net torque counterclockwise should equal 0. So this all means the same thing for this case. Okay, so what we want to do then is plug in these equations. Okay, so let's go ahead and plug in what we know for these motions. So here I'm going to say my clockwise is going to be let's see, our right hand force, or I'm sorry, torque, our right hand torque, sorry. And we would put our left hand torque here too, but we are saying that that is 0 since that's our pivot point, equals our counterclockwise, which is going to be our torque of the weight. Okay. All right, so then from there, this is for A, I should have put that somewhere. Okay, from there we can say TR is going to be our radius, and that is from hand to hand, so that's going to be R1, times our force, F sub R, okay, times sine theta equals, I should say, what is our sine theta here? Let's see. So that should be our 90 degrees, right? So this is just going to be 90 degrees. Okay, time equals minus our torque of our weight here. So that's going to be R2, okay, times our weight, and sine, and that is going to be our negative 90 again, okay? Okay, so now we can plug these things in and solve for FR. Okay, so that is going to give me -1. So it should be R2 over R1 times our W, which is mass times gravity. Okay, so 0.9 over 0.6 times our mass, which is 5 kilograms, times acceleration due to gravity, and that should be 73.5 newtons. Okay. All right. So that is for our first part here. We know the force that the right hand is exerting. Now we want to know the force of the left hand. Okay. And now instead of using this part of equilibrium, let's go ahead and use the other part of equilibrium, that the net force should equal 0. Okay, so what we should have is that, well, we know that everything is in the y-axis, or the y direction, so this would just be net F sub y equals 0. Okay, so we have F sub R plus F sub L minus our weight should equal 0. Okay, so FL should be W minus FR. And we can plug these things in. So our mass is 5 kilograms times our gravity is 9.8 minus FR, which we just solved for. Okay. So let me go ahead and plug that into my calculator. So this minus 73.5. Yeah. Wait. Okay, I made a mistake up here when I was plugging in my values. Here and here. Okay, so the reason I was able to catch that is because that this was going to give me a negative value, and that wasn't going to make sense since it should be in the positive direction. Okay, so let me go back and plug these in. So R2 is 0.6 and R1 is 0.9. Okay, let me try that again. So 0.6 divided by 0.9 times 5 times 9.8. Okay, there we go. So we get 32.7 newtons here. Okay, so let's plug that in. Okay, that makes more sense. 16.3 newtons. Okay. All right, so again, I made that mistake and that threw my value off, but thankfully I was able to catch it from that. And so my force exerted by my right hand is 32.7 newtons, and my force exerted by my left hand is 16.3 newtons. Okay. All right. I'm gonna go ahead and stop this, and then we will go ahead and go forward with our next example.